Hi, everyone. I'm Carson Cristiano from SIGA. I'm the executive director of the Center for Effective Global Action. Apologies that our lunch break was cut very short. Hopefully you've had a chance to grab a bite to eat at some point. I'm going to go ahead and get started with our next session. We've packed a lot into today and a lot of exciting talks to come. So thanks a lot to Mokhtar and his team at the bank's infrastructure VP for entrusting us as co-hosts. I hope everyone's enjoying the talks today and learning a lot. I'm here to introduce two more keynote speakers. Both are SIGA affiliates based at UC Berkeley. They're using new types of data and new analytical tools to measure infrastructure development and track a range of related outcomes in data-sparse environments. Professor Catherine Wolfram will discuss efforts to green the electricity sector in the developing world, drawing on insights from randomized evaluations that she's running with colleagues in Ghana, Kenya, and the United States. Saul Xiang will talk about a low-cost scalable methodology that he and his team have developed, which uses machine learning and satellite data to remotely estimate outcomes related to climate change as well as socioeconomic development. I encourage you to ask questions during both of these keynotes by typing them into the Q&A box at the bottom of your screen. And please note your affiliation so that speakers know who the question is coming from if you can. We'll reserve 5 minutes at the end of each talk to answer your questions live. And if we have any questions remaining, the speakers will have the ability to respond to you in writing through the Q&A box in the Zoom. So we're going to start with Catherine. Catherine Wolfram is a leading expert on energy and environmental economics. She's the Cora Jane Flood Professor of Business Administration at the Haas School of Business, where she also serves as Associate Dean for Academic Affairs. She is Program Director of NBER's Environment and Energy Economics Program and an affiliated faculty member in the Agriculture and Resource Economics Department, as well as the Energy and Resources Group at UC Berkeley. Catherine, please go ahead.
Great, thanks so much, Carson. Just starting my screen share here.
Looks great, thanks.
You can see it?
Yep.
Okay, great. Yeah, thanks to Carson and thanks so much to Mokhtar and Vivian and the whole World Bank team. This is a superbly important topic, so I'm thrilled to be part of this conference. What I wanted to do is start by sharing some thoughts on kind of global trends and opportunities in decarbonization, and then I'll do a deep dive on one particular research project that I have. So I wanted to start with an example that I know well. I'm sitting in California, so this is a graph that's looking historically and showing some progress on decarbonization. I thought it'd be useful to start with kind of an optimistic view. And I'm going to show you a number of graphs that have the same form. So let me go over what's going on here. I'm plotting the trend in California's greenhouse gas emissions since 2000. And basically the graph is normalized to be 1 in 2000. So you can see that California's greenhouse gas emissions increased through the early 2000s, by about 5–6%. And then we passed the landmark piece of legislation in 2006, the AB 32. And after that, our greenhouse gas emissions started to fall. So this is total emissions that are going down. Our economy has continued to go up, to rise. This is not normalized by economy, not normalized by population, but our total greenhouse gas emissions have fallen by almost 10% since 2000. This, as I said, has reflected a lot of hard policy work. We now in California have the highest electricity rates of the whole continental US. So this has not been easy, but we have accomplished this. By way of contrast, I wanted to also look at US greenhouse gas emissions since 2000. So as I say, it's the same graph normalized to 1 in 2000. And you see that US-wide greenhouse gas emissions have fallen by more than in California. They've fallen by almost, say, 13% since 2000. I think this is an important point as we start to think about decarbonization, because the US, especially post-2016, it's not on the graph here, but especially with the Trump administration, there has not been policy interest in reducing greenhouse gases, but they have continued to come down. And what this reflects is some profound market impacts. So there's been huge coal to gas switching as a result of the reduction in natural gas prices because of fracking. And so this has led to some very profound reductions in greenhouse gas emissions. As I said, post 2016, largely absent federal policy. Another example in interest of Professor Michael Grubb, the UK. So here you've seen even greater reductions in greenhouse gas emissions since 2000, over 30%. And I would say, you know, if California was policy and the US was market forces, the UK has been some combination of market forces and policy. Early on, they benefited from low gas prices and there was coal to gas switching, but there have also been some profound policy changes. The UK participates in the EU emissions trading system. As Michael indicated, there's been a lot of investment, a lot of money spent. They've closed every coal power plant in the whole country, and so achieved some pretty serious emission reductions. And again, just to emphasize, this is total emissions which are going down. I'm not normalizing by anything. All right, so I think in the spirit of this conference, I wanted to dig into these emissions reductions a bit and start with the UK. So this is separating emissions by sector and zeroing in on transport and electricity. And together, transport and electricity, especially back in 2000, accounted for more than 50, close to 60% of total GHG emissions. But what you see is really two different emerging stories. You see that in electricity, there have been extremely large emissions reductions, more than 50% reduction in emissions from the electricity sector in the UK relative to 2000. By contrast, the transport sector, you know, it started to come down with the global recession in the late 2000s, in the late aughts, but then started trending back up. And on net, the reductions in UK transport-related GHG emissions by 2018 has only been on the order of about, you know, say 5%. And so to me, this just tells really different stories by sector. This is a point that Mokhtar made at the outset. So we're going to have to really double down on thinking about ways to reduce GHG emissions in the transport sector. But for reasons that I'll get into in a second, we do not want to give up on the electricity sector. There are important reasons to continue reducing emissions in the electricity sector. Okay, so just to make the point that this is not just a UK phenomenon, this is a very similar graph from the California sector. So again, the kind of bluish green line is electricity sector GHG emissions, and the red is transport. The transport line looks almost identical to what you saw in the UK, you know, on net about 95% reduction in GHG emissions by 2018, or sorry, only about 5%. The emissions are at 95% of what they were in 2000. But in the electricity sector, pretty profound reductions. The one thing I will say about the electricity sector emissions in California is they are quite volatile. Like a lot of countries in Africa, California's electricity generation relies a fair amount on hydro. And so basically our GHG emissions go up when there are droughts and are much lower when we have ample hydro resources. Recently, though, we've installed a lot of the cheap solar panels that people have been talking about, primarily are both in the desert at grid scale and on rooftops. And this has been a large part of the recent emission reductions that California has experienced. So my husband works in the electricity sector in California and often comes home and says, they're just breaking the back of the electricity sector. You know, we got to think about some of these other sectors. We need to think about reducing emissions in transport. And I do think we need to think about reducing emissions in transport, but we cannot give up on the electricity sector. So just to kind of put a fine point on the scale of the problem that we're looking at. So I plotted California, the US, and the UK, where we've seen reductions in GHG emissions since 2000. But by contrast, in other parts of the world, mainly in the emerging markets, we've seen dramatic increases in total GHG emissions. And just to emphasize, this has been accompanied by even more growth in gross domestic product and GDPs. So economic activity has accompanied these rising GHG emissions, which is important and certainly not something to lose sight of. But the GHG emissions increase in China has been over a factor of 2.5. So more than doubled GHG emissions in China since the year 2000. Africa, almost a 50% increase in GHG emissions since 2000, and in India, almost doubled GHG emissions since 2000. So transport and electricity sector there are growing and sectors that we need to be paying keen attention to. Okay, so given the divergence in the red line and the green line on the graphs that I showed you for the UK and California, where we've seen dramatic reductions in electricity sector emissions and not such dramatic reductions in transport, I think it just emphasizes the point that there are huge opportunities to learn more about decarbonizing transport. And so I welcome forums like this to think hard about what those opportunities are and to start thinking about this from both a policy and a research perspective. But we definitely have to keep the pressure on the electricity sector. Why do I say that? There is an emerging consensus that the most effective way to reduce emissions from the electricity or from the transport sector, starting with personal vehicles, but at some point moving to commercial vehicles, is through electrification, either direct electrification like this Tesla that you see here, or through techniques that people have talked about in the earlier panels, like using electricity to make hydrogen and using the hydrogen to power commercial trucking vehicles. So the thing about the Teslas is right now, I took this picture from the Tesla site, and Teslas are being marketed to people who live in houses that look like this, very upscale homes, possibly in Silicon Valley. So people are at the very high end of the global income distribution. But what we need to think about is how to get Teslas and electric vehicles into places like Nairobi. I've taken this picture, I think, from a newspaper from Kenya. And so there you see the bodabodas, you see the trucks, the buses, the matatus, so a variety of different vehicle types that we need to think about electrifying. We need to think about the traffic, the congestion issues that are present in big urban centers in emerging markets. But importantly, we also need to think about the infrastructure that's supporting this transportation electrification. And so these are the growing and increasingly strained electricity sectors in sub-Saharan Africa. So if you're going to think about electrifying transport, you need to think about the source of the fuel. You need to think about the electricity in this case. And in my view, the electricity sectors in emerging markets face some unique challenges. So it struck me that in forums like this, there's a term used, electrification. It's the exact same term that's used in many of the discussions about decarbonization in California. But in those contexts, in the California context, electrification means something very different. So in context thinking about emerging markets, electrification is about access. How do we expand the national grid? How do we think about solar mini grids or solar home systems? How do we get first-time users of electricity access to the service? Whereas in California, the term electrification is changing the energy source. It's about electrifying transport or electrifying buildings. In my city, Berkeley, they have forbidden new homes from using anything but electricity for cooking. We've outlawed natural gas from cooking. So that's the electrification that is on the table that's being discussed in California. And so I think that this really emphasizes that there are different issues that are facing the electricity sectors in emerging markets, and that we need to continue to do research on these issues and think hard about these issues. Another issue that I think is somewhat unique to emerging markets is reliability, and I'll talk about this in a second, although California recently has been experiencing some fire-related reliability issues. Also, issues of kind of the utilities incentives, the state-owned utilities in a lot of cases, the issues around their solvency, and issues of losses, technical and non-technical losses. This is something that is uniquely an issue in electricity sectors in emerging markets. And then we get down to issues that are very important about rate structures and how you set prices to incentivize use of electricity as the scope for electricity use expands into areas like transportation. What the wholesale market dynamics look like, capacity markets. These issues are front and center to the discussions of electricity in places like California, and are indeed important to think about in emerging markets, but I think we also need to think about these top three issues. So what I want to do in the remaining part of the talk is say a bit about some work that I'm doing in reliability, and I think this is going to hopefully provide a nice transition to Saul's talk, because it's talking about measurement and talking about ways of acquiring data. Okay, this probably doesn't need to, a point I don't need to make to this crowd, but often when I'm talking to crowds in California or in other parts of the developed world, I need to emphasize how important reliability issues are to consumers of electricity in emerging markets. So this is a picture of a billboard from just outside the airport in Nairobi. It's an advertisement for a refrigerator. And the refrigerator is being, the primary feature of the refrigerator that's being advertised is its ability to sustain blackouts. So it's saying, for 10 hours it will last, and it's got the longest cool air retention. So I think just a poignant example that reliability is front and center to how people think about consuming electricity and how people think about buying appliance markets. So in order to think hard about reliability, as researchers, as policymakers, as utility companies, we need to have data on what that reliability looks like. And so here's a map that's thinking about one indicator of reliability. It's called the SAIDI, or System Average Interruption Duration Index. And it's plotted for the whole world. So basically think of this as a metric of the number of hours of outage that customers experience throughout a typical year. So according to this map, the US, Western Europe are in the kind of low single digit range. In the US, I think it's about 2 to 3 hours of interruption on average per customer per year. In Germany, I know it's a lot lower than that. It's about less than an hour. But what this map really highlights is, for one, the areas where you're on the high end of disruption, so on the order of, say, 500 hours of interruption per year, are in emerging markets. So places like Kenya, Nigeria, Pakistan. The other thing this highlights, though, is that a lot of emerging market countries, there is no data. That's what these dark gray scale indicates. And I showed this picture in a conference in Ghana recently, and people were highlighting that the DRC looked to be the same shade as the US, but they were very suspicious that that did not reflect accurate data, that in fact reliability issues were more profound in the DRC than this graph represents. So I think this highlights both the lack of data, explicitly with these grayscale countries, and potentially the lack of high quality data. And so I've highlighted 4 countries here. These are countries where I'm working with a team of engineers from UC Berkeley to think about measuring reliability and think about acquiring better metrics of reliability. I have one slide on the technology. I'm happy to direct you to the engineers themselves for more details on the technology, or happy to talk about it in the Q&A. But basically the idea is to use the cellular network as a way to capture data about how well the electricity system is working. And what's going on is that the sensing devices that the team of engineers has developed are picking up information both from smartphones and from some custom devices. They're calling them PowerWatch devices, which we're deploying in, now we're up to about 1,500 houses and businesses in Accra. And then kind of assembling all the information from these sensors through cloud computing and using the information to draw inferences about the outages that people are experiencing. I think importantly, one thing I'll say about the technology is that it does not rely on cooperation from the utility companies. It's something that we deploy at the customer level, and so is independent of the utility company information. So let me just give you, one kind of tidbit of the types of information that we're gathering in Accra from these devices. So what I'm showing you here is another metric of outages. This is about frequency of outages, not the duration of outages. And I'm showing it to you here for 3 months in 2018 in one district in Accra, in the Achimota district. So this is what, at first I'm going to show you what the utility data are telling us about the outages in this district, and then I'll show you what our GridWatch data shows you. So basically this suggests that there are on average something like 2.8 outages per customer in this area in July, similar in August, slightly more in September. If you break that down, ECG, the utility, has identified that a lot of those outages are at the 33 kV system or higher. So what we would consider high voltage outages. So, either a big failure at a substation or some kind of load shedding. There's a much smaller component that it's at the medium voltage level. And then, you can probably barely see this, but there's a tiny green sliver here, which are the outages that they've identified that are associated with the low voltage network. So this is the information that the utility company is collecting. This is the information that they're using to make decisions about how many upgrades to do and where to deploy their trucks. So let me show you what we're seeing from the GridWatch devices. And I'm dividing it here, oops, shoot, I gave away dividing it here between large outages and small outages. So in terms of large outages, ones that are presumably on the high or medium voltage network, the GridWatch devices see very similar outages to the utility. And the utility now has a SCADA system that's measuring the outages on its high and medium voltage network. And so this is kind of comforting that GridWatch is capturing the same level of information. Maybe slightly more outages GridWatch is seeing. Maybe this reflects this was early days and the engineers are still kind of tuning their algorithm, or maybe it reflects a little bit of underreporting in outages on the utility side. But what's really profound is that we see about double in July the number of outage associated with the low voltage distribution network. And so this is outages that just aren't captured by the utility data. And as I've emphasized, just cannot be factoring into the utility's decisions about how to deploy its resources. It's just something that the utility does not have visibility into. And so I think this is a really important indication that obtaining better data is going to be important, to utility companies to make decisions about how to deploy their resources. It's important to people like me, to researchers who are studying reliability. We need to have accurate on the ground estimates of reliability, and important to donors. We are working on this project with the Millennium Challenge Corporation, who's spending hundreds of millions of dollars to improve the reliability infrastructure in Ghana. And so they need to be able to measure both the before and after impacts of their investments. So I guess I want to conclude by just thanking SIGA and the World Bank again. This is, I said, is an extremely important topic, and it's really important to get researchers together with policymakers. I wish it could be in person. Hopefully, we can get together in person in the future and think about ways to make progress on these issues. Thank you.
Catherine, thanks so much for your talk. That was great. And I really appreciate the nudge to not give up on decarbonization of the electricity sector, despite progress that's already been made. I think we're not going to have time for live questions, unfortunately, but there are a couple questions in the Q&A box that I'll direct you to. And one of them, which I think is interesting, is regarding, why have we made so much more progress on electricity than we have on transport? And could, increasing demand for transportation outweighing decarbonization in that sector be part of the explanation? So I think you've also perfectly teed up our next talk by emphasizing the need for reliable, low-cost data on conditions happening on the ground. So with that, I'll transition to our next keynote speaker. And Catherine, you can go ahead and turn your video off. Solomon Shang directs the Global Policy Laboratory at UC Berkeley, where his team is integrating econometrics, spatial data science, and machine learning to answer questions that are central to rationally managing planetary resources. Sol is the Chancellor's Professor of Public Policy at Berkeley, a co-director of the Climate Impact Lab, a research associate at NBER, a National Geographic Explorer, and an Andrew Carnegie Fellow. So Sol, go ahead and share your slides.
Great. Thank you so much for having me. This is such an exciting conference, and there's so many cool projects being shared today. Today, what I wanted to show is a way in which we are collaborating with actually a team in the computer science department at Berkeley to try and make existing global infrastructure available to users around the world who could, exploit it or benefit from its usage in a variety of problems where we don't think it's been applied. So what we're trying to do is, there's so many satellites in space right now. We constantly are seeing images from space and all sorts of news reports or different types of studies. And in fact, they're pulling down over 100 terabytes of data a day. This is actually a visualization of the satellites in orbit. So we have all this infrastructure that's out there. We should be using it to achieve the sustainable development goals, tackle different types of global challenges. But one of the issues that we realized is that, there's many ways in which complicated analytical procedures are being applied to this data. Machine learning is being used to create really high resolution, interesting maps. But every time one of these maps comes out or one of these studies is executed, it's a major research enterprise where you have people who are experts on satellite imagery, working with people who are experts on machine learning, who are domain experts. And the problem is this kind of slows down progress so that many individuals who could use these types of technologies, who could exploit this global infrastructure we've already built, don't have access. And so this project started from the notion that, users everywhere, people who may not have as much sophisticated training as an elite research team at a top university, should be able to use this material. So, for example, here's a woman who's on an anti-poaching team in Botswana. She definitely could benefit from having better surveillance power that would help her do her job and conserve species in her region. So we asked, how could this be achieved? How could we lower the barriers to entry? And what we realized is we need to really make something that anyone with sort of basic statistical training, basic computer resources could use. And then could they take those resources, take those skills and apply them to using satellite imagery combined with machine learning, which is what we call SIML. And it's sort of this large class of technologies of using machine learning to extract structured information from satellite imagery. So what we did is we built a system, which I'll try to show you. It's now operational, that we call the multitask observation with satellite imagery and kitchen sinks, which has the clever acronym of being called mosaics. And the key appeal of what we're doing is that, first of all, it's really easy for users to exploit the system. So an individual with very little training basically has to download some data and run a linear regression. It's also computationally very cheap. So you can do it on a personal computer or a laptop in a matter of minutes. And as I'll show you, it achieves really good performance. It actually performs essentially as well as sort of deep learning models that are sort of state of the art at the moment. And one thing that we think is important philosophically, especially for this community, is it allows us to understand the uncertainty in how the system is performing, because we're going to use these for different types of decision making. So the basic idea of our system is that when you look at these different types of satellite images, when we look at an image, each user looks at the image from a different perspective. So for example, we have 9 images here, and one individual might be interested in thinking about forest cover, and so they would rank the images in one dimension. A different individual would look at the images and be interested in looking at how many people are living in the image. And so they'd be looking in a totally different dimension. And so what we wanted to do is take all the imagery that exists and sort of organize it, pre-organize it in a way so that any individual could take the data and kind of look at it from their own perspective and extract the type of information that they are trying to look for. And so the way it works, this is a very simple cartoon, is you have a bunch of images like so that you know where they're located in space. And what we do is we take these images and we turn them into basically a table of features. These are like X's that you would have in any kind of regression model. This is a table that could be downloaded in CSV form, where there's basically a row for every single image. Now, these features are hard to interpret. They wouldn't make sense to you if you were to open it up, but they're very useful, because what you can do is, say you're an individual and you have some observations on the ground that you are trying to match and trying to, extrapolate to other locations. So you have these observations on the ground of forest cover, you match them to the features of the corresponding locations, and you run a regression, right? So you estimate some coefficient on these features. And then what that lets you do is, if you took this coefficient and you applied it to the locations where you didn't have original data, you could generate a map, okay? And so this allows you to exploit the existing satellite infrastructure and the data that an user one has to generate a map covering a much larger area. Now, what's nice is that this table of data generalizes. It can be used by many different users. And so a different user interested in a different problem can take the same table of data, download it, match it to their data, run their own regression, get their own unique betas, and then when they do their extrapolation, they get a map of whatever outcome they're trying to study. And so the whole point here is to recognize that there's this shared infrastructure, these satellite images that everyone should be able to use to solve totally different problems without having to go back to basics each time and trying to learn like machine learning from square one. Now, the key to making this all work is this embedding here, which literally is a black box in the diagram. And the basic idea, without getting into the details, the paper's public, so anyone interested can take a look, is we basically go to every single image and we extract little sub-images, and we compare every sub-image in every picture to every sub-image in every other picture. And the basic idea for why that works is, when you look at a building in one location kind of looks like a building in another location. So if you're trying to count buildings, you can just compare all the different sub-buildings. But the reason we do it for all different pieces of images is because we don't know what future users are going to look for. So this kind of has the effect of pre-organizing all the images in lots of different ways so that users can say, well, I'm interested in the stuff that's associated with buildings, or I'm interested in the stuff that's associated with population centers. And whatever it is that you're looking for, it's somewhere in this table of features. It's also really nice because it's very fast. And so we wanted to test both how fast it is and how well it works for doing a bunch of different problems. So we took it to the United States, and we actually work in the US first because we're very interested in going to the developing countries where there's less infrastructure for data collection. But we felt like it was really important to go to an environment where we actually knew what was right and what was wrong, where we had really good data so that we could rigorously evaluate its performance before going to a context where it would be then used for decision making. So we take it to the United States, and what I'm showing you here is two things. So on the bottom is basically the sequence of steps a user would take in order to use the material. So you basically would merge the data. You have some tree cover data, you merge it with this table of X's, you run a ridge regression, and you do some prediction. And so on the left is the training data, on the right is validation data. And so what we see is we get really high performance when trying to look across the continental United States at tree cover. And what's cool is we then take the same set of variables without doing anything differently, and we can predict population density at a high level of fidelity, again, across the United States. We've run it on a whole bunch of different problems. So we take it, we try to predict elevation. Turns out using just a daytime image, we can estimate elevation quite efficiently without knowing any information about where the image was taken from. And we can also use daytime imagery to predict how bright a location is going to be at night. So nighttime luminosity, which has been the topic of many prior studies. And in fact, we can even look at house prices. So for example, just looking at daytime images, the same thing that looks at population density or predicts elevation can help us estimate what the average house price is in a square kilometer. We've also done it for road length and other types of infrastructure. So I think we're doing additional analyses right now to figure out what else we can see in the energy system, which would be relevant, I think, for this audience. And of course, we're interested in other types of socioeconomic variables, things like income per household, which we've pulled from the census. And so what's exciting here is that we have a single table of data that basically you could download in Excel and run a regression in Stata or R, or whatever your software is, and it works for all sorts of different tasks. So then the other thing to think about is that the resolution that it achieves is pretty remarkable. So here I'm just showing you Rhode Island, and across the top are predicted values. And in fact, I'll explain in a sec, but it has the feature of actually improving on existing data in many cases. So for example, here's nighttime lights, and it's actually got a lot of atmospheric disturbances, but we are actually able to localize where the light is coming from so that the predictions that come out of mosaics in many cases are higher quality than the original data. Now, people often want to use the best available technology. And what is exciting is that mosaics performs really well. It performs similar to a deep learning model, even though the main benefit of mosaics is that it's so much cheaper to use. So for example, if you had access to a GPU and you were going to use like the ResNet model, it would take you about 8 hours to train, whereas mosaics takes about 2 minutes on a laptop. And so we think this is a really important step towards making this technology accessible to users everywhere. Not everyone has easy access to a GPU or knows how to run these other more sophisticated models from scratch. And so there's a little bit of a performance hit, but the big benefit is that everyone can use it for different types of problems. Now, we also are able to do different types of evaluation of performance, which are important for policymaking. So in many cases, we don't actually, have ground truth data to verify against. And so we wanted to ask, okay, if we're in a region where we don't have that kind of information, how can we simulate that and ask how well we will do? So we invented this experiment in which we took the country and we chopped it up using a checkerboard. And we said, okay, let's train the data on the white squares and then try to extrapolate to the black squares and ask, as we change the size of those squares, how does performance improve or deteriorate? And so, for example, looking at forest cover, what we see is, the benchmark performance when we're kind of not dropping the checkerboard is pretty high. And then as we start pulling out checkerboard regions of the United States that are getting bigger and bigger, we see that actually the performance stays very, very good. Now, that's not true for all tasks, but for forest cover, it's certainly true. And we compare this against other types of procedures people in the field are using. So for example, if we do some cross-validated interpolation, it just gets worse and worse over time as the checkerboards get bigger, and bigger. So we can do this kind of evaluation for different types of problems and evaluate, given that we're going into a region that's this large for which we don't have data, what kind of performance do we expect to achieve? And we think this is really important, especially because going forward, we're talking about maybe giving households money based on, what they look like from an image. We should have some sense of uncertainty in terms of those metrics. I think that's important for policymaking. Now, ultimately, the goal here is not just to predict stuff in the United States that we know, we want to go global. And so here was an experiment in which we asked how quickly could we do it? And we were very excited that we achieved similar performance looking at imagery from around the world. In many cases, actually pulling out, so here on the left are the actual labels, on the right are predictions for 1 million sample points around the world. And we did other experiments where we were trying to simulate how users, maybe like folks here at this conference, might interact with the data. So we said, well, what if someone wanted, didn't have access to a census? Could we like recreate a census, something like what we have in the United States? So we took the ACS, and actually one member of the team took 1 week and essentially predicted 12 variables from the US Census, from the American Community Survey for the entire US. Now, we're not achieving an R-squared of 1, like this is not the same as having access to the census. That is superior data. But what's nice is that instead of spending, it cost the US roughly $500 million to deploy the census each time, the ACS each time. And so this is a much cheaper alternative that is going to be useful, we think, in many contexts where a better alternative is unavailable. We've also taken into some classic problems. So for example, predicting wealth in here, Cote d'Ivoire, and we achieve similar performance to other teams working with much more sophisticated models. And then one aspect of the approach that was very exciting for us is that because it's such a, it's a simple approach where the model itself is actually linear, we were able to understand what was going on inside the model and realized that we should be able to do better than the original training data. And so what we do is demonstrate that we can achieve something that's called super resolution in the literature. So basically the raw data we have describes an area the size of this square over on the left. So like forest, we know the average forest cover or the average population density. What we can do with mosaics is we can actually localize where the forest cover is in the image by using information from the image. So we end up being able to generate outputs that are higher resolution than the original data that was put into the model to train what was going on. Similarly, you can see we can estimate where in the image the population is located, even though we only know average populations for the entire square.
1 or 2 minute warning, Saul.
Yeah. So right now we're in the process of building an API to make it so the paper's public. Anyone can see our method. And
I put a link in the chat.
Oh, great.
To the paper.
And so we're building an API like as we speak to make it so that anyone can essentially download this table of data, because that is really the key to having access. And then anyone can just match it to their data and run a ridge regression and solve whatever type of problem they are trying to tackle. And so, the overall philosophy here is that we have already invested in a tremendous amount of satellite infrastructure. It should be used to address global challenges. And machine learning is really the tool that's opening the door, allowing us to transform that unstructured imagery into usable structured data. And right now, the last step is to make it so that stakeholders around the world can actually access that complex technology, given the skills and tools that they have. And so Mosaics really aims to achieve this by having a simple approach that is generalizable for all sorts of problems. That means it works essentially out of the box, even for problems that the model hasn't seen before. And to date, based on the experiments we've done, it appears to achieve performance very competitive with state-of-the-art deep learning models. And then finally, for this group, we do think it's quite important to have tools that are this fast and simple that we can really understand their uncertainty, especially because these tools will be used for making critical decisions. Thanks a lot.
Awesome. Thank you, Saul. This is extremely exciting. It sounds almost too good to be true. Can you talk very quickly about how many decision makers in low and middle income countries you suspect might already be using machine learning to extract information from satellites? I'm guessing the answer is pretty close to 0.
So we have talked to many people and we keep getting the same answer, which is this looks really cool. We just don't have the resources, the ability to do it. And so I think right now there's a lot of people sort of chomping at the bit where they want to be able to use these tools, but they just don't, everyone's stretched pretty thin already. So experimenting with a new technology is always quite costly. So we're working in partnership with many groups right now to try to figure out how to make the system as usable as possible. But we really hope that, this can open the floodgates.
That's great. I'm sure we could spend a whole hour or more talking about what the next steps are here. So thanks a lot, Saul. That was great. And before we transition in about 10 seconds, since we're talking about satellite data, I'm going to make a very quick plug for a symposium and workshop that SIGA is hosting in a couple weeks. This is also joint with the World Bank and an organization called New Light Technologies. It's called Geospatial Analysis for Development. Or Geo for Dev. So we're going to hear during the symposium on December 10th, we'll hear from SIGA affiliates Marshall Burke and Josh Blumenstock and a bunch of other folks from some from the bank. And then on the second day, it'll be a hands-on workshop focused on applying the nighttime lights data to development research. So I'm going to be putting the link in the chat right now. So thanks everybody, and we'll move to the next session.